Last year. Yeah.
Okay, that's not so weird.
Yeah.
I thought you meant today. And I'm
Okay,
Yeah.
so let's go ahead and make our table.
Me too.
Well, what do I have to do first, I guess?
Derivative.
Derivative. What do we
Negative
get?
sign.
Negative sign.
Wait, you forgot the mark. You broke.
Okay, so then
Then
we need to know where the critical numbers are, right? On our domain. So what do we find? So we need to know where what are the two kinds of places where critical numbers occur when the derivative is
zeros
points.
and undefined.
0 and undefined, right? Is sine theta ever undefined anywhere?
I said any.
No.
No. Sine theta is well behaved, it's defined everywhere, so we have none of that to worry about. But where does it equal 0 on this interval?
At 0 and 1?
Sine equals 0 where on the unit circle?
0.
0 and,
Negative.
okay, so on our interval, we're going from negative pi 6 to pi, so the interior critical numbers would just be 0, right? Everybody agree? So then we can make our table. So there's the x-axis, right?
Maybe that.
That's supposed to be an x. Oh man, it's even worse.
Wow, nailed it.
This thing just,
Nailed it.
So when we're doing an absolute extrema problem with the table, it's pretty simple, right? All we're gonna do is just identify critical numbers. Well, the first derivative is, so we're going from negative pi 6, put the closed, the square bracket there to indicate that that's a closed endpoint, up to pi, and at 0, the first derivative was 0, right? What do we do now?
1 and 0.
Just check the second row, right? We're just checking the values of the function at those three places and see who the winner and the loser is, right? So what do we get? Cosine of negative pi 6 is going to be, what is that, square root of 3 over 2,
Yep.
Yeah.
right?
Yeah.
Well, it's right there, right? You know that.
Yeah, that is.
Cosine of 0 is,
Can we refresh that too? The little trick that you did. I already forgot that.
the little, you guys remember the
You
trick?
use your thumb,
it's
right?
Who remembers the trick? Tell us the trick. It's a great trick, right?
So-
Show us the trick.
Start at 6.
No, stand, come stand, show us
Yeah,
the trick.
tricks.
Preach it.
Attention. Okay, so you take your hand, and this is the first quadrant, and if you're on the line, which is your thumb right there, that's 1. Wait, not 1. It's 1 right here. 1 and 0. Because just shh.
Just kidding.
So if you skip like the endpoints, if you go for the middle parts, so like for the first 3 dots, right here is for your parentheses, you have the
Square root of
Square
2,
root.
you're always comparing the
Yeah.
two, right?
so you just go like whatever. You just use your fingers to do it, and you just like move your
Okay.
hand based on where you are. And I don't know how I remember it. Just
What?
does.
Okay, so I'll fill in a couple of blanks here.
I
So-
showed you the trick. I'm
So
not
if
explaining.
we're on the x-axis, right, then this is the thumb, right? So that's telling us that to the x values are going to be it's the square root of 4 over 2, right? Is the coordinate of that point. Does that make sense? You're always taking the square root of the number of other fingers. See what I'm saying? Divided by 2. What's the square root of 4 is 2. Divided by 2 is 1. So the x coordinate is 1. Okay, the y coordinate is going to be what's on the other side, which is 0. Square root of 0 is 0, right? Over 2 is just 0. So the coordinates at that point are 1, 0. Okay, let's go here to that one, right? So then the x coordinate is the square root of 3 over 2, and the y coordinate is the square root of 1 over 2, right? Which is just square root of 3 over 2 and 1/2, right? If we go there to the middle one, I get the x coordinate is the square root of 2 over 2, the y coordinate is the square root of 2 over 2, right? See how that works? It's cool. And then here we'd get, at this point, we get the square root of 1, which is 1, so x coordinate is 1/2, y coordinate is square root of 3 over 2, right? See how it works? And then for that one, x coordinate is 0, y coordinate is square root of 4, which is 2 over 2, so it's 1.
It's the same thing, you just switched the size.
Isn't that cool? That's just super cool. I love
They
that.
should have taught this to us last year, like
Yeah,
seriously.
you should tell us.
Had
Jones.
unit triangles.
Freaking
Freaking unit triangles.
Can we just take a field trip into Jones and be like?
No, no,
Hey,
hey,
now,
You know, I learned this, I only learned this a couple years ago. It was just something I taught forever and didn't, it just someone brought it to my attention.
Unit triangles too?
So at, what's the, at 0 then? What's the cosine? 1, good. And at pi, cosine is
-1.
-1. Okay, well, what's the biggest value? 1. What's the smallest value? Done. How about that?
English,
Right?
So it's just like, what's French? Espanol.
Okay, so I'm gonna skip this for now because I want to get to better stuff. Okay, because this is, once again, this is just absolute extreme. No big deal. Same deal as before. Okay. I wonder if we should look at that one. 2/3. There is something kind of cool about that. Let's do one more. Let's do this one real quick. How about? So f of x equals, write that down. I'll forget. Write down this stuff. I remember it. Just remember it. You guys just want to remember it.
That's what I was thinking.
So what's that prime?
2/3 x -1/3.
2/3 x to the -1/3, you said?
Yeah.
So I'll just write it like that. Okay.
Fancy.
So are there any places where the first derivative equals 0?
Probably.
Where? Because now let's think about this. We're going to talk more and more about this. But whenever you're analyzing a function, a rational function, where you've got, it's a fraction, right? Where is the fraction? What part of the fraction determines where the fraction equals 0? The numerator, right? So we would just ask, where is the numerator equal to 0? And the answer is
Nowhere.
nowhere. It's never equal to 0. Okay. We'll soon discover that we can take a limit where its value approaches 0. Right? Actually, we already probably could do that, but we'll learn more about that soon. We're going to do an infinite limit section like tomorrow or Friday, probably Friday. Where the function is undefined, in this case, this is an odd root, right? So we don't have to worry about the even root part, but it's where the denominator equals 0. And where does the denominator equal 0?
0.
It's 0, right? Because we could say that 3x to the 1/3 equals 0 when x equals 0. Right, when x to the 1/3 equals 0, which is at 0. So we end up with one critical number at x equals 0. When we make our table, we can even do better than that, right? We can even kind of show what kind of critical number is it, right? So we've got f prime, -1, 8. We get one critical number at 0. And it's the kind where this is undefined. And I think rather than writing U, I used to write U and D. Let's just go ahead and write U for undefined. Okay, so then all we have to do, same as before, is just check the values at all 3 of those places. Our one interior critical number and the 2 endpoints, see what the winner is. No big deal. Okay, what's going on there, do you think? Why is that a critical number? What about this interesting discussion topic here. Where do derivatives not exist?
Sharp corners.
Sharp corners?
Holes.
Any place where, any place where the function's undefined, right? Or the limit's undefined. But there's one other one too. Breaks in the function, right? That's not what's going on here though. No. Vertical tangents, right? Remember that? That's a kind of one you don't see very much. That's what's going on here. If I let x approach 0, would you agree that the slope is going to infinity? Right?
Yeah.
As the bottom approaches 0 and the top stays at 2. We'll talk more about this later, but you get the idea? Okay? So, yeah, so it's approaching infinity, and in fact, that ends up being a vertical tangent. And so that's why the derivative is undefined there. And hence you get a critical number. Okay? All right. Okay, new stuff. Okay, so here's the other stuff. Oh, what am I doing? Okay, so this is just some integrals. You guys remember us talking about that, right? No, we haven't talked about that. I hit the wrong one.
I think they're about February 26th or something like that.
Yeah.
See it.
Yeah, that's the wrong one. Okay.
Well, it said 4.1, I think, or something.
Yeah, I was
Yeah,
gonna
wait a
look it up
second.
and see what it was.
There we go.
Show up my next year's paper.
Chapter 3 test on March 9th.
No, that's not, I don't know why that number, that's not right though.
I like the number. One right.
Okay. Oh, these are the ones from the book. You have any questions from the book, from those questions? I think you're probably I want to skip up to 3.2. And actually, even 3.2, that wasn't even a big deal, was it? Wasn't 3.2, isn't that just the
That's a
mean
great
value
question.
theorem, or
3.2 and 3.3.
Can we look at number 3?
on which one?
The 3.1.
On-
It's problem 12.
Okay, yeah. Problem 12.
Wait, 3.1 part 2?
Yes.
3.1 part 2, number 12.
Oh.
Also number 12.
Okay, so that's this guy. Okay. You said number 12? Okay, and we're just supposed to find critical numbers, is all we're supposed to do. How do we find critical numbers?
Derivative. Or the chart.
Yeah. Differentiate. Okay, so, yeah. Okay, so f prime, what's this term gonna give us?
Two.
Secant theta. Okay, you guys gotta, so if you don't remember those well, memorize them tonight, because I'm gonna give you a quiz. We gotta know those. You can't be worrying about thinking about those. It's gotta be instantaneous. Okay, so we gotta find critical numbers. So where is that undefined and where is it equal to 0? How are we gonna do that? This relates to the last, this is a good one, glad you brought this up. This relates to the last problem that we did.
Just stick it equal.
So there's a couple ways you can look at this. A function is undefined where any part of the function is undefined. So you could look at it in that way, okay? But I think what I always prefer to do is I always prefer to try to write this as a single rational function. So what if we wrote this in terms of sines and cosines? Okay. So then we'd end up with secant is 1 over cosine and tangent is sine over cosine, right? So we'd get 2 sine theta over cosine squared theta from the first term, everybody agree? Plus secant squared would just be 1 over cosine squared theta. Well, those are common denominators, right? So we can add this up and just get 2 sine theta plus 1 over cosine squared theta. How about that? This is good for a couple of reasons. What's one reason that that's a good idea?
It's not done in unison.
Well, there's, no, it's not really. See, I can see what you're looking at. It's not really, but there's something else about this that's just inherently good.
Once we find when cosine squared equals 0, then we can.
Okay, so part of it is we've got it written in rational form, so we can just say, okay, it's undefined where the bottom equals 0, and it's 0 where the top equals 0, but there's another little part of that I want you to appreciate. These guys are kind of nasty, secants and tangents. Why are sines and cosines inherently easier to work with and better than
Unit
those?
squared.
Graphs are,
Okay, what's going on?
the graphs are, they have closed intervals and they have jumps.
Okay, good. The graphs of every trig function except sine and cosine all have asymptotes, right? So they're all going to be parts of their natural domains where they're undefined, right? Does that make sense? That's a mess, having to think about all that stuff, right? Having to think about where tangent or cotangent, I mean, it's not that big a deal, but it's just one extra layer. We'd rather not have to worry about it. Sines and cosines just wiggle forever. They're well behaved. So we don't have to worry about the players in this expression having, you know, their own problems, right? The sine and the cosine are fine on their own. It's just the fraction now that we can focus on. Where is the top equal to 0 and where is the bottom equal to 0? The sine and the cosine individually are fine, right? So it's going to be f prime equals 0 when the top is 0, right? Everybody agree? And this is that other thing we kind of talked about. It's been a while, but mathematicians, this is a good strategy. Instead of having to treat something in its complicated, full-fledged form, let's just pick out the key components here. This is equal to 0 when the top equals 0, which is when sine theta ends up equaling what?
1/2.
Negative 1/2, if I isolate the sine theta. So that's just a unit circle issue, right? On the unit circle, from 0 to 2 pi, where is sine theta equal to negative 1/2?
Negative root 3 over 2.
So there's negative 1/2. Sine is a y value, isn't it? Right? So it's going to be right there and right there, right? Everybody agree? I've got, think about the different values at our key points on the unit circle. The coordinates are either going to be 0 and 1, we can just, those are obvious. But the other ones, if I write them in order from smallest to biggest, it's 1/2 square root of 2 over 2 square root of 3 over 2, right? We know that's going to be, this point right here, all we need to remember is that it's a negative big X, small y, right? So the small y is 1/2, right? So that's going to be how far beyond pi? 5 over 6, right? So that's just 7/6 pi. And this is how much less than 2 pi? Pi 6. So that's 11/6 pi, right? You follow, is that making sense? So then this is, on our domain, that's at 7/6 pi and 11/6 pi, right? Okay, how about where f prime is undefined when cosine is equal to 0, right? Where's cosine equal to 0? That's x, right?
Oh. Instead, 1 and 1.
So right there, right? Pi halves and 3 halves pi. So we got how many critical numbers then? 4. Plus endpoints. I would just line all those up on my table and check it. Make sense? Right? Make sense? If we're looking for absolute extrema. Okay. Okay, so I'm gonna get rid of that guy then. And let's go down. I guess we should probably, for today, why don't we just wrap up looking at 3.2. This is just the mean value theorem stuff, right? This is no big deal. Okay, so maybe let's just, before we even do this, let's just look at the mean value theorem. It's an existence theorem also. That's all it is. It doesn't do any of the work for you. It just tells you if something exists or not. What's the mean value theorem say? Remember this one, the mean value theorem for derivatives. It's a picture theorem. Mean value theorem just looks like this, right? It just says if I've got if a function is what on a closed interval from A to B? Smooth, good. Continuous and differentiable. We can combine those. Our book doesn't do it, neither book does it, but it's a great math word, smoothness. If it's continuous, it means I can draw it without picking my pen off the board. If it's differentiable, it means it has none of those places where the derivatives are undefined. Primarily, we're concerned with sharp corners, right? So I can draw it, and I can never scrape my hand if I brush my hand on the function, right? Okay, we'll finish this up tomorrow. And then we'll do new stuff on, what's today? Wednesday? So we'll do new stuff on Friday.